Today I would like to talk about Google. I'm assured that all of you use Google. In fact, it's not really a question. I mean, is anyone using any other search engine, really? It's the search engine. So I think that we all have a cultural image of what the search result page of Google looks like. Up at the top, you've got your search terms. Directly below that, you've got various filters. Below that, you have something that says about X million results generated in less than a second. It's kind of miraculous, you know? And below that, you have all of your X million results. Well, you don't have all of your X million results. You have about 20, and then you have to go to another page. They don't seem to be alphabetized either, or like organized like a library so that it's easy to find what you're looking for by specifically scrolling through this system and finding the right author or whatever. It's not like that at all. Instead, these web pages seem to be sorted in a different way. That's what my speech today is going to be all about. I want to talk about the PageRank algorithm created by Google to sort its various pages. So to begin with, I want to talk about what PageRank is based upon. Back in 1996, Larry Page and Sergey Brin, creators of Google, decided to create a system where more popular links would float to the top of a search results and less popular links would float to the bottom. Now, intuitively, you might say, well, that's easy enough. We'll just use internet traffic. Seems easy, seems convenient. You know, the more people who visit a website, the more likely that website is to appear in your top 5 search results. This isn't exactly true. Actually, what they based PageRank on was on what's called link popularity. All link popularity is the idea that the most popular and relevant information will be cited on multiple places throughout the internet. So, let's take Wikipedia as an example. Most Wikipedia pages have a pretty good PageRank score. And the reason is because Wikipedia pages are a lot of citations citing other places in Wikipedia, which are giving those other pages additional weight. Thus, Wikipedia will always be in at least the top 5 of any particular search you do about something on the internet, if there's a Wikipedia page relevant to it. There are sort of two big advantages. Well, there's one big advantage, one key disadvantage to this whole thing. The big advantage to using this link popularity system is that it creates a fairly stable base of search results. You're going to see more or less the same things week to week for a particular search. Things aren't going to change too drastically. Maybe you'll see some new links, but not a lot. And that's pretty good. We like that. It means that, you know, if you search up something one week, you come back, you search it up again, you can find it instantly. It's great. Unfortunately, the downside to it is that newer websites really have a hard time getting any kind of traction. Newer web pages can't really climb up in the ranks because they're just not cited as much. They have to stick around on the internet, and there's this big seniority thing going on. Over the years, people have tried to cheat this system. For instance, there are what are called link farms. From what I understand, link farms are large collections of web pages, and the service they offer is that you can pay them for them to post a link to your web page all over their website. We'll see in a minute how Google has actually combated this. But first, I want to jump into giving you a visual example of how we can start beginning to build up to the PageRank algorithm. So imagine you have a web search that turns up 3 results. We'll call these results A, B, and C. Now, if we look at just these, I want to ask you what you think the probability would be that a random surfer would randomly click on one of these three links? It's kind of immediately apparent. All you would have to do is take 1 over the total number of nodes in that particular network, and you would get an even distribution throughout all of these links. So, in this case, 1 over n is going to equal 1 over 3, and each one of these is going to have a 0.33 chance that someone will click on it. Now I want to start making this network a little bit more complex. To begin with, let's say B and C are both have links on them which link to A. Now this is going to mean that A is going to be a whole lot more popular than B and C. So how do we get the new page rank for A? Well, we can start off by just adding the weights of B and C together. So the page rank of A is going to equal 0.33 plus 0.33. So it will equal 0.66. Now, I want us to examine a different scenario. Let's say we have a network that still looks exactly like this, except that B also has a link to C. Now, from what I've shown you, if you were just to calculate this as is, you would say, oh yeah, it's the same thing, it's just 0.66. But it's not. Whenever we have a case in which one website has multiple outbound links, we're going to have to take its weight and divide it by the total number of outbound links. So, instead of PRA is equal to 0.33 plus 0.33, we're going to have PRA is equal to 0.33 divided by 2 plus 0.33. So then, our new result is going to equal 0.165 plus 0.33, which is equal to 0.495. So we can see that A's rank has gone down a little bit. Instead of a score of 0.66, we now have a score of 0.495 because B isn't giving over its full share. It's giving some of that weight to C. Now we can begin drawing a more general formula for what's going on here. We can see that here we've got the sum of all links connecting to a particular web page. So our formula will look like the page rank of some web page X is equal to the sum of all links Y that are elements of Z, where Z is some set containing only those websites with links to X. So PRX is equal to the sum, where Y is an element of Z, of the page rank of Y divided by the total links coming out of Y. before I continue on, there is something I'd like to note. There are a few illegal moves here. For instance, you may wonder, well, what happens if a website cites itself? Let's say C cites itself. Or let's say B has multiple links to A. In this instance, for PageRank, loops and parallel edges are always eliminated. This is to prevent those link farms I was mentioning earlier. So now we've got this formula, right? It looks pretty good. It's a pretty nice formula. It's it's pretty. It's got a sum in there. That's always nice. But we're not quite done yet. We still got a little farther to go. Because mind you, when we were looking at those initial values, 0.33, we considered them to be 0.33 because of the chance that you would end up clicking on one of them. Well, now we're going to have to start thinking about something else. Sergey Brin and Larry Page decided that they would also include in their formula something about the chance that someone would continue surfing. Of course, there's always a chance that someone will stop surfing on the internet and quit their search, go to someplace else. They wanted to include this somehow in their formula. So they created D. Now what D stands for is, D stands for the damping factor. And Larry Page and Sergey Brin decided that the damping factor would be equal to 0.85. So what is the damping factor? The damping factor just suggests that there is an 85% chance that someone will continue clicking. That if someone visits a website, they will click on a link and continue to another website. That they will continue this surfing pattern. How do we add D into our newfound formula? Well, first and foremost, we're going to multiply D onto our sum. However, there's one other thing we do, and it's adding a whole nother term. Remember when we did that initial thing where we were like, oh yeah, the page rank of A is equal to 1 over N? Well, we're going to add in something similar here, which is the condition in which someone stops. That 0.15, that 15% chance that someone stops is also something we're going to factor into this algorithm. So, for this one, we're just going to add 1 minus D all over the total number of nodes in this network. We're still not quite done, though this is certainly a perfectly acceptable algorithm. This is the algorithm that's cited in the 1996 paper they wrote on it. This is the algorithm that's more or less used, but it doesn't really describe what's going on when it gets down to computation. So now I want to take a look at that. How will we compute this sort of thing? Well, it's all iterative. It's all based on time steps. At each time step, Google is going to go through the entirety of its search results and change each number based on previously found values. Initially, at time step 0, we're going to have the formula one over n. Now, at time step 1, and every time step after that, 1 to infinity, I suppose, we're going to have an alternate version of this formula up here. Now we're going to have the page rank of x semicolon t plus 1 is equal to d times the sum where y is an element of z of the page rank of y semicolon t all over the total links going out of y plus just our good old function 1 minus d all over n. So now it's looking a little more massive. It's this big long thing, but really all it's saying is that we're going to base each step on the step before it. Now I want to run through sort of a brief example of this, since this is the completed formula, and show you for some example how this might work. Let's say we have our values A, B, C. Now, let's say B has connection to A, C has a connection to A. Hell, let's do the example we did previously, but in full. B has connection to C. So already, because this is a fairly simple thing, we can see that hopefully what we'll end up with is that the rank of pages will be A first, then C, then B. So let's start a table. This table is going to have the value t for time step, and the page ranks for each of our values. So initially we know, of course, that our first thing we do is 1 over n. So all of these values at time step 0 will have 0.33. Well, 0.33 repeating, but basically 0.33. Now, at time step 1, we're going to we're going to start looking at those values we just established. So, let's start off with A. We know that the two things pointing to A are B and C. We know that B's weight is divided by 2 for the number equaling 0.165, and C is also pointing to A, but C only has one outgoing link, so we have our 0.33, which will give us a total result of 0.495. Next, we're going to want to multiply. Next, we're going to want to multiply this number, 0.495, by 0.85. Got a calculator here, gonna do it, 0.495 times 0.85 gives us a score of 0.42. Next, we're going to want to add in 0.15 over 3, which is going to equal 0.05. Seems pretty simple. 0.42 plus 0.05 is equal to 0.47. Next, we're going to look at PageRank B. Now, something interesting happens here because PageRank B doesn't have anything connected to it. It has there are no links directed towards B. So that original term, that sum, is going to sum up to 0. It's going to be meaningless. No, instead we're just going to use the value of the 1 minus d all over n. So that's 0.15 divided by 3, which is going to equal 0.05, and that's going to be our new value for the PageRank B. It's really low. And finally, we've got our PageRank of C. Now for C, we see that we've got one connection from B to C. We know that that connection has the value of 0.165, and there are no other connections, so we're going to want to multiply 0.165 by 0.85, which will get us a result of 0.14. So then 0.14 plus 0.05 is going to equal 0.19. Now we can keep going, but already we see that there is this ranking having been established. I'd like to go through one more time step just to make sure we've got sort of the idea down of what we're doing. So, once again, for the PageRank of A. For the PageRank of A, we look at half of B plus the whole of C. So we're looking at 0.025 plus 0.19, which is going to give us a grand total of 0.215. Yes. 0.215 now multiplied. 0.215 now multiplied by 0.85 is equal to 0.18. 0.18 plus 0.05 is equal to, God, what is that? 0.23. We can see a pretty big decrease in its page rank, but as we'll soon see as we go through the rest of these, it still remains on top. PRB, we still have no links that connect to B, so really it's just going to stay the same score. We're still going to have 0.05. And then PageRank C. For PageRank C, once again, we have only one link connecting to C. It happens to have the value now, a very, very small value, of 0.025. Now we're going to multiply 0.025 by 0.85, and we get the result of 0.021. We're going to add to that our 0.05, giving us a total of 0.071, or in this case just 0.07. Now we could keep going, but I think that we can all see that C is always going to be greater than B, and that A is always going to be greater than both C and B. This is the formula that is used to sort all of those web pages that you see throughout the internet. What amazes me is its simplicity. It's a really nice formula. I know my handwriting is probably atrocious, but what I'm going to do is I'm going to put up a link with this video, if you all have made it through, so that you can see the math more clearly. I'll put up the algorithm, I'll put up each of the steps to get to the algorithm, all that sort of thing. Anyway, I hope you enjoyed, and if you have any questions for me, feel free to comment below. I hope this has inspired you to think more about the things we take for granted, such as Google. And yeah, y'all have a wonderful day. Thank you.